Next up for us is capillary action, another property that is heavily influenced by intermolecular forces. Now, I'm going to be honest, most of the time when we talk about capillary action, you're going to see it in like a biology class more than a chemistry class. I'm going to show you a very short clip of a video that shows it in action, but it's essentially this: like if you put a paper towel and you get one edge of the paper towel wet, you'll see that over time that water kind of creeps along the paper towel, and eventually, if you had enough water to begin with, the whole thing gets wet. Likewise, if you take a really, really, um, uh, you know, thin tube of glass and you put it into a liquid, you'll see water rise up the sides of the glass, and it has important biological implications. That's why we talk about it in that class. But it's essentially governed by intermolecular forces. Biologists use different words, so I will introduce those. We know that water molecules are connected to each other by hydrogen bonds. What we haven't really talked about very much is that water can be attracted to other water molecules, but it certainly can be attracted to other things as well. So, for instance, to the sides of a container, it's going to stick to it a little bit as well. So, if you look at the picture over on the right, we have a group of water molecules, and they're starting to climb up the surface of the glass container that they're in, or the glass tube that they're in. In biology, the word that we use for, if this right here is the glass surface that it's trying to stick to, and the water molecule sticking to it, that is called adhesion. It's essentially when water molecules stick to the surface of something else, in this case, like a glass tube. And when water molecules stick to one another through like a hydrogen bond, like down here, this is a hydrogen bond, biologists would call that cohesion. We don't really use that word very much. But since it's a biological topic, we'll use some of their words. So we have all of these water molecules held together through cohesive forces that we know as hydrogen bonds. And we have water molecules that are essentially trying to climb up the sides of the container through adhesive forces. Now, you'll notice that essentially in water, that creates a special thing called a meniscus. And the meniscus in water is such that it's higher over on the edges than it is in the middle. And there's meaning for that, and we'll discuss that meaning here in a minute. But I want you to compare it to its next door neighbor, mercury. Mercury is a metal, but it's a liquid. It's held together not by hydrogen bonds, but by metallic bonds. Okay? And if you look at mercury, the forces that hold I'm struggling with my pen, sorry. The forces that hold those mercury atoms together seem to act differently than we see in water. Okay. The meniscus is exactly the opposite of what we saw for water. And so here's a question that I want you to think about for the next time we get together here in a couple of minutes is, what can you say about the cohesive versus adhesive forces and their strengths in both water and in mercury? And why would they essentially be opposites? Okay, it's a thing to think about, and we'll discuss here in a moment. In the meantime, I'm going to show you a very short clip of a video that just shows capillary action happening. Okay, we'll see you in a couple minutes.